In the autumn of 1915, French infantry officers along the Western Front began receiving wooden crates marked with unfamiliar designations. Inside each crate lay something the world had never seen distributed at such scale: a fully automatic rifle light, enough for one soldier to carry and operate independently. The Fusil Mitrailleur Model 1915 CSRG, soon universally known as the Chauchat after the commission chairman who shepherded its development, represented an engineering response to a tactical crisis that traditional hardware design couldn't address. The crisis was simple to describe, but unprecedented in scale. Across hundreds of miles of entrenched lines, personnel faced an impossible dilemma. Advancing across open ground toward opposing positions meant exposure to sustained rapid fire that could neutralize entire waves of infantry within seconds. Yet those heavy machine guns, mounted on tripods and requiring multiple crew members, couldn't accompany units during an advance or provide flexible support in fluid tactical situations. Bolt-action rifles, the standard infantry equipment, required users to cycle their actions after each shot, a critical delay when facing automatic fire. What military theorists recognized was a fundamental gap in the tactical toolkit. They needed sustained fire capability that could move with individual soldiers, something that provided the suppressive power of a machine gun, but with the portability of a rifle. The French called this concept walking fire, the ability to advance while maintaining continuous output that could suppress defensive positions. The engineering challenge was creating such a tool using manufacturing infrastructure already strained beyond previous peacetime capacity. Louis Chauchat, a career artillery officer promoted to colonel, led a military commission tasked with solving this problem not theoretically but practically, with a tool that could enter production within months, not years. The commission understood that perfection was the enemy of sufficiency. They needed a design that worked adequately with the industrial tools, materials, and workforce actually available in 1915 France, not the precision manufacturing capability that might exist in more industrialized nations. The equipment that emerged embodied radical compromises in service of a single engineering goal: mass production of mobile automatic power. It used stamped metal components rather than forged steel. It operated with the existing 8mm Liebel cartridge already in French logistics chains. It required simple machining operations that semi-skilled workers could perform using available equipment. When the first Chauchats reached frontline units, personnel didn't receive a perfect tool. They received something far more valuable in that moment, something that existed in sufficient quantity to change tactical possibilities. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far. And stay with us for the next chapter. Colonel Louis Chauchat faced a paradox that defined wartime engineering: create innovation while eliminating uncertainty. The commission he chaired in 1914 included Charles Sutter, a civilian designer, and military representatives who understood that any automatic rifle design would need to satisfy not only ballistic requirements, but also constraints that peacetime engineers rarely confronted. The French army needed hundreds of thousands of units, not hundreds. Traditional precision manufacturing methods couldn't scale at that rate, with the nation's industrial capacity already committed to artillery shells, rifles, and machine guns. The pressure intensified with each report from the front. Rapid-fire systems dominated defensive positions, but their weight and complexity meant each infantry division possessed only dozens of these tools. Light, portable automatic capability didn't exist in organized military inventories. Several experimental designs had appeared before the conflict: the Mexican Mondragon, the Danish Madsen, but none had been adopted for mass service. And more importantly, none could be manufactured quickly using simplified processes. Chauchat and Sutter made their first critical decision by accepting the 8mm Liebel cartridge as a non-negotiable constraint. This round, with its pronounced taper and rimmed case, created significant feeding challenges for automatic equipment. The cartridge's geometry demanded curved magazines, and its rim meant each round had to be positioned precisely to prevent mechanical malfunctions. Most designers would have specified a different cartridge, something with a straighter profile and rimless design. But specifying a new cartridge meant establishing new production lines, new logistics chains, and new training protocols. The Liebel round was what France had in vast quantities. The second decision defined everything else. Use long recoil operation. This mechanism, where the barrel and bolt traveled backward together before unlocking, was mechanically simpler than gas operation systems, requiring precision-drilled ports and complex piston assemblies. Long recoil needed fewer precision-fitted parts and could tolerate looser manufacturing tolerances. The trade-off was weight and a somewhat ungainly mechanism, but those disadvantages mattered less than the benefit of simplified production. Sutter's technical drawings showed a tool built primarily from stamped sheet metal and simple turned components. The receiver could be formed from steel sheets that required bending and welding rather than precision milling from solid blocks. Internal components used basic shapes that semi-skilled machinists could produce on standard lathes. Even the controversial open-sided magazine, later criticized for debris vulnerability, emerged from manufacturing logic. Stamping those distinctive half-moon curves was far simpler than forming a fully enclosed magazine body, and the open sides actually served a practical purpose. Personnel could visually confirm their supply count without removing the magazine. By early 1915, the commissions submitted their design for military trials. The tool wasn't elegant, and it certainly wasn't refined by peacetime standards, but it met the only standard that mattered. It could be produced at the rate modern global conflict demanded. Understanding how the Chauchat works requires recognizing that its mechanism prioritized reliability through simplicity over efficiency through complexity. At the moment of activation, the barrel and bolt assembly were locked together as a single unit. The long recoil system's fundamental principle was that these two components would travel rearward together for a substantial distance, approximately 14 centimeters, before any unlocking occurred. This approach differed fundamentally from short recoil systems, where unlocking happened almost immediately, or gas operation systems where the barrel remained stationary. The sequence began with the trigger releasing the striker to ignite the cartridge. As expanding gases propelled the projectile down the barrel, those same gases exerted equal pressure in all directions, including rearward against the bolt face. Because the bolt was locked to the barrel through a rotating mechanism, the entire barrel bolt assembly began moving rearward against the resistance of the recoil spring. During this initial phase, both components moved as one unit, with the barrel sliding backward inside the receiver, while the bolt remained locked. At the rear of this recoil stroke, the tool's geometry forced a rotation. A cam track machined into the receiver engaged with a stud on the bolt, causing the bolt to rotate approximately 20 degrees. This rotation disengaged the locking mechanism, separating the bolt from the barrel assembly. The sequence timing was critical. Unlocking occurred only after pressure in the chamber had dropped to safe levels as the projectile exited the barrel and residual gases vented. Once unlocked, the barrel and bolt followed independent return paths. The barrel, driven by its dedicated recoil spring, began traveling forward immediately. As it moved, the extractor claw mounted on the bolt pulled the empty case rearward, withdrawing it from the chamber. An ejector mechanism then removed the empty case through the side of the receiver. Meanwhile, the bolt remained held rearward briefly by the internal mechanism, creating the timing delay necessary for complete barrel return. When the barrel reached its forward position, the bolt was released. A second spring drove the bolt forward along its path. As it moved, the bolt's face contacted the top round in the magazine, stripping it from the feed lips. The bolt's forward momentum pushed this fresh cartridge into the chamber. In the final millimeters of travel, the cam track again engaged the bolt stud, rotating the bolt and locking it with the barrel extension. The tool was now ready for the next cycle, with the entire sequence taking approximately 1/10 of a second. This mechanism's genius lay not in theoretical elegance, but in practical tolerance. The long recoil stroke provided time for complete pressure dissipation before unlocking, reducing stress on components. The positive unlocking cam meant that weak springs or fouling wouldn't prevent proper cycling. The geometry physically forced the rotation. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The first field trials revealed what engineers already suspected. Theory meeting reality always produces surprises. Testing began at French proving grounds in early 1915 with prototype tools manufactured in small batches by skilled craftsmen using precision methods. These prototypes performed adequately, cycling through magazines and maintaining reasonable accuracy at standard engagement distances. The Commission documented acceptable functioning under controlled conditions with clean ammunition and regular maintenance. Reality arrived when production-grade units began emerging from the rapidly established manufacturing facilities. Components that worked perfectly when hand-fitted by skilled craftsmen now came from stamped sheets and simple operations performed by workers with minimal training. The tolerances were looser, the fits less precise, and the surface finishes rougher. Early production units displayed inconsistent cycling, with some functioning reliably, while others experienced frequent technical issues. The engineering team traced many issues to tolerance stacking, small variations in individual components that accumulated into problematic misalignments when assembled. The solution wasn't tightening specifications, which would have defeated the entire manufacturing strategy. Instead, Sutter's team redesigned critical interfaces to accommodate greater variation. They enlarged clearances in the bolt path, modified the magazine catch geometry to accept magazines with wider dimensional variance, and adjusted spring specifications to provide more consistent force across the manufacturing range. The distinctive half-moon magazine became the focus of intensive revision. The open-sided design, chosen for manufacturing simplicity, allowed dirt intrusion that could cause feeding issues. Engineers experimented with partial covers and redesigned feed lips, but each modification added complexity and cost. The final production magazine retained the open sides with modified internal geometry that improved reliability despite not eliminating vulnerability to extreme contamination. The engineering decision was explicit: accept this limitation rather than delay production for a perfect solution. Bipod design underwent multiple iterations. Early versions proved too fragile for field conditions, bending or breaking under the tool's weight and recoil forces. Revised designs used heavier gauge materials and improved attachment points, trading a slight weight increase for durability. The barrel length, initially specified at 470 mm, was reduced slightly after testing showed minimal accuracy loss, with shorter barrels that reduced overall weight and improved handling. By mid-1915, production accelerated rapidly. Multiple facilities across France manufactured components using the simplified processes the design enabled. Quality varied between production batches, but the tools generally functioned adequately for their intended role. Field reports indicated that properly maintained Chauchats provided the mobile automatic capability that units desperately needed, despite requiring more frequent cleaning than standard rifles. The American experience later in the conflict introduced additional complications. American forces initially used French 8mm Chauchat tools, but logistical considerations led to an attempt at adapting the design for the American 3006 cartridge. This modification proved highly problematic. The more powerful cartridge stressed components beyond their design limits, and production quality for the American version was notably inferior. The resulting issues created a reputation for unreliability that historical accounts often applied to all Chauchat variants, though the original 8mm version performed substantially better. The final curiosity that defines the Chauchat's true significance emerges from production statistics that seem to contradict its notorious reputation. Between 1915 and 1918, French manufacturers produced over 262,000 Chauchat automatic rifles. This figure represents more units than any other automatic tool manufactured during the First World War, more than the Lewis gun, more than the Hotchkiss, more than the Madsen. The tool that history often dismisses as a failure became the most widely distributed automatic rifle in human history up to that point. This paradox reveals the essential truth about wartime engineering. Adequacy at scale outweighs perfection in scarcity. A tool that functioned reliably 80% of the time, but could be produced in unlimited quantities, provided more tactical capability than a tool that functioned 95% of the time, but existed in numbers insufficient to equip every squad. The Chauchat's manufacturing simplicity meant that France could equip its forces with automatic tools while simultaneously producing millions of standard rifles, thousands of machine guns, and vast quantities of heavy support. The magazine design, so often criticized, actually embodied sophisticated engineering compromise. The half-moon curve precisely matched the geometry required by the 8mm Liebel cartridge's taper. The open sides, while admitting debris, also provided visual confirmation of supply status, a practical field advantage that closed magazines couldn't offer. Personnel could glance at the magazine and immediately assess their remaining rounds without the need to remove and inspect it. In difficult conditions, where situational awareness meant survival, this transparency had genuine value. Field maintenance protocols evolved to accommodate the tool's characteristics. Units learned that the Chauchat required more frequent cleaning than standard rifles, but far less maintenance than belt-fed systems. A trained user could disassemble the tool in under 2 minutes, clean the critical components, and return it to service. The simplicity that enabled mass production also simplified field maintenance. Fewer precision-fitted parts meant fewer catastrophic points of failure. The tool's true limitation wasn't mechanical unreliability, but contextual appropriateness. The Chauchat functioned adequately in its designed environment, relatively clean conditions with regular maintenance and properly manufactured 8mm Liebel ammunition. It struggled in extreme contamination with poorly made ammunition or when modified beyond its design parameters, as the American 3006 conversion demonstrated. This pattern appears repeatedly in engineering history. Designs optimized for specific conditions face challenges when applied to circumstances beyond their original parameters. The Chauchat's legacy extends far beyond its service years, shaping automatic equipment development in ways that remained invisible until examined through the lens of engineering philosophy rather than battlefield performance. The tool demonstrated that mass production techniques could be applied to complex mechanical systems previously reserved for precision manufacturing. This lesson proved foundational for subsequent designs throughout the interwar period and into World War II. Engineers studying the Chauchat recognized that its failures and successes both stemmed from the same source: radical prioritization of manufacturability over refinement. This approach influenced designers of later tools who faced similar constraints. The Soviet PPSH-41, produced in millions during World War II, employed stamped metal construction and simplified mechanisms that directly descended from lessons the Chauchat embodied. German designers creating the MP40 similarly embraced stamping and simplification after recognizing that precision-manufactured equipment couldn't match wartime demand. The tool also revealed the critical importance of matching ammunition to hardware design. The struggles with the 8mm Liebel cartridge and the issues with the 30-06 conversion taught planners that logistics and engineering must align from the earliest phases. Interwar development, including programs that eventually produced the American M1 Garand and the Soviet SVT-40, explicitly considered ammunition characteristics as primary design constraints rather than secondary accommodations. Perhaps most significantly, the Chauchat established the tactical category that military organizations now call the automatic rifle or squad automatic weapon. Before 1915, infantry doctrine divided equipment into individual rifles and crew-served systems. The concept of a portable automatic tool that one person could operate while moving, the walking fire capability, didn't exist as a formal tactical category. The Chauchat, despite its limitations, proved this capability's value. Every modern military force now fields equipment in this category, from the American M249 to the Russian RPK to the Belgian Minimi. The tool's reputation as a failure reflects a common historical distortion, judging engineering decisions by peacetime standards when those decisions were made under wartime constraints. The Chauchat wasn't designed to be the best automatic rifle theoretically possible. It was designed to be the best automatic rifle actually producible in sufficient quantity to matter strategically in 1915. By that standard, measured against the constraints and requirements of its specific historical moment, the project succeeded. Modern engineering education increasingly uses the Chauchat as a case study in constraint-driven design. Students learn that optimal solutions emerge from understanding limitations rather than ignoring them. The tool demonstrates that acknowledging manufacturing constraints, ammunition limitations, and tactical requirements can produce designs that succeed precisely because they accept imperfection in service of practicality. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.